Now, the last time we saw, we saw this was common criteria where we finished, and then we were supposed to start from what are the basic capabilities of systems as far as how they try to protect themselves, right? So if you look at any information system, right, today, the IT system forms part of the overall information systems, and few inbuilt, processes, inbuilt systems which are there to protect a system are flashed on the slide. Okay, first is memory protection. Now, what happens is you don't give access to memory directly. Okay, there are three classes of systems. Once you look at the computer architecture, the RAM is something which is used by the operating system, right? You do not have direct access to the random access memory. You can give certain allocations, but you do not have access to the random access memory. The random access memory is part of the operating system's work. Okay, the operating system might employ many techniques to protect the memory. Okay, the OS, the kernel, okay, and the memory, and the the CPU, they form part of actually the entire what we saw last time, secure reference monitor. So the OS has complete control over the memory. It does not want to part away that control. Okay, and whenever you, as a developer or someone who's interacting with the system, tries to uh, you know get elevated access to the memory, right, then also the OS protect itself. Okay, it has very, very dedicated memory spaces on where the kernel will write, where a particular application will write, where a particular device will run. So that is how it protects the memory. Okay, it might protect the memory by virtualization. So how do you protect the memory by virtualization? One way is you access a system directly. Okay, you have your CPU here. Okay, you have your RAM here, and the operating system is right now residing in the hard disk. You get the operating system loaded into the RAM, okay, and then execute it inside the CPU. This is one way. Okay, second way is, what you do is you virtualize. What you do, you make the CPU feel that there is a memory available to the CPU, and it is forming the core. Okay, now CPU does not come to know what it is doing. It forms a small operating system, minor operating system on top of this, and then whatever is happening in a virtual environment. Now this is a architecture of Windows, 2011, 2000, yeah, 11 Pro, or Windows 11 Pro, right? This is how Windows 11 has been designed. You do not have access to the memory and the processor directly. You have to go through a virtualized layer. Okay, so you're protecting. You're doing everything in a virtual way, right? Then you have TPM. What is a TPM? TPM is uh, it's a uh, it's a cryptographic module. Okay, it's a small cryptographic module. So earlier, what used to happen, say you want to uh, surf a website, right? If you're surfing a website, what used to happen was the keys were stored in the browser itself, okay, or in an application which was sitting on the hard drive. Nowadays, what happens is the TPM is a trusted module. Okay, it's a trusted protection module which is designed to keep the secrecy keys in a manner where nobody can have access to these keys. So what happens is, say you have a laptop wherein you're using your fingerprint. Now, earlier days when TPM was not there, the fingerprint module will go and get stored. The Once you scan your fingerprint, okay, it will be converted into some digital data, and it will go inside some file in an encrypted manner and go on the hard disk. Okay, where it becomes accessible. You can get access to someone can get access to that, right? Now that was not a good arrangement. So the concept of TPM was evolved and implemented. Okay, trusted protection module was implemented using a hardware storage device. So what happens? This is the hardware storage module in which the TPM is employed. So what happens is your CPU and your RAM and your TPM, whenever an application needs some kind of keys, the keys are fetched by the CPU from the trusted platform, and this TPM forms part the OS kernel plus this HSM and plus certain device drivers. They form part of the overall TPM. The HSM module stores the keys. Okay, all keys, whether you are browsing a website, that private key is stored inside this HSM module. Am I clear? Any doubts? Okay. Together, the operating system, the HSM, and the OS, they form the trusted computing base or the trusted platform module. Okay. So you have to understand this concept. Okay. So once, okay, then you also have to protect the interfaces. So what interfaces does a IT system has? It has a network interface, right? So you have to protect this network interface, and mainly one of the major ways in which you protect, data at storage and data at rest is using encryption and decryption. Okay. Okay. Now, whenever you are designing a system, okay, say you have a project at hand wherein you have to start developing a system, which let's say we are developing UIDAI, right? The Aadhaar, right, system. So now what would have, the entire teams would have done? They first would have gone into what is the computer architecture. Okay, what kind of computing architecture is required? How will we have this secure design elements, that is right from the collection of the data, okay, and to the movement and to the storage, how this complete thing will be secured. Okay, so you have to implement security, you have to understand security right from the start, from even the conceptualization of a particular project or an architecture. So because if you don't implement security architecture right from the beginning, you don't consider what are the threats, what are the vulnerabilities, and what we have done till now in domain one, diagramming and assessing. If you don't do that, if you don't apply it to a project, then you will have to build security afterwards. Okay. Now, in the cloud, security is a shared responsibility. This was something which was asked, last time, that who is responsible. So there is a shared responsibility in the cloud. In the cloud, we all know, most of us know, there are three models. One is infrastructure as a service, one is software as a service, and one is platform as a service, right? Now, what happens infrastructure as a service is the entire infrastructure, you build it. Hypervisor onwards, there is the responsibility of the cloud service provider. Above it, whatever infrastructure you bring in, whatever infrastructure you churn, is the responsibility of the client or the customer. Okay. In platform as a service, what happens? Your hypervisor is there. After this comes the operating system and the libraries which are required. After this, the application comes. The libraries and the application, okay, are generally, libraries are told by the customer, but maintained by the cloud service provider. The main responsibility is of protecting the application and how it handles the data. That remains with the customer. And in software as a service, you have no responsibility other than protecting the login to the application. Rest everything is handled by the service provider, right? So this is called the shared responsibility model. Now, once we look at security architecture and we discuss what is shared responsibility in cloud, we understand that. But even in on-premise system in your organization, security is everybody's responsibility. It is just not CISO who is responsible for security. It is everyone, right from the top to the bottom. Okay. Now we will see some common vulnerabilities and some common ways in which information systems are built, so that we are aware that how it protects itself. Okay. So whenever a processor executes, right? So how a computer system works is, for those who are not from the engineering background or who have not seen this particular domain till now, right? So how a system works is, you have your CPU, right? And you have your primary memory, and then you have your main memory, and you have certain your storage device, and you have input output functions. Input output is your keyboard, your printers, your network devices, right? Now whenever you want computer to execute something, what happens is you give it some input, okay? And that input is received by the CPU, and based on that input, CPU tells what needs to be done. Okay, so it might tell that, okay, fetch. So it has certain more logical units. Those logical units might fetch some data from the storage to the primary memory and then execute it in the CPU. But if you look at computer system, what you see is there's so many applications being performed by the CPU at one time, right? How does it do it? Okay, now earlier days the CPUs were single core. Okay, one single core. That means there was one input bus and there was one output bus. Now what used to happen is, a stream of data is going, CPU is processing it and giving it out. Okay, whenever some other application, so this is application 1, okay, now application 2, if it comes in, what used to happen was, application 2, if it has got higher priority, if its priority is higher, application 1 will be pushed into a memory and asked to wait. It goes into waiting state, and application 2 is brought inside the CPU. Okay, now imagine if there are 100 such processes happening. So what CPU used to do, it used to do what is called time division multiplexing. What is time division multiplexing? It says, okay, I'll divide my processor time into small refresh rates and handle each process for 1 millisecond or 2 milliseconds. And the speed at which the CPU used to do, we used to call it its CPU's, processing frequency or processing power. And that was given as 2 megahertz. Then it became 100 megahertz. Okay, then it became 1 gigahertz. Now it is 2 gigahertz. Then it is 3 gigahertz. Now we have reached up to 18 gigahertz. That means the CPU is capable of processing this information at a frequency of 18 gigahertz. Okay, so that is the broadly how CPU works. Now what happens is, a CPU nowadays doesn't have one single core. It has 2 cores. It might have 4 cores. It might have 8 cores. Okay, it might have 16 cores. And it has the each core is actually a kind of a CPU. Okay, you can build one single computer on top of it using VM. Okay, so what happens if you take such a large server, you can actually have small servers running over it by creating VMs. On each core, you can create one VM. And that is how on-premise infrastructures are being used by companies to have their own private cloud kind of an arrangement. They don't want to immediately move to cloud because they have so much of server systems where they can run multiple processes using different virtual machines. Okay, now this kind of an arrangement is something called multi handling of computer systems, and that is of different types. Okay, first is called multitasking, when you are executing 2 tasks, okay, simultaneously. In this case, you just have one processor. We had 2 tasks. Okay, you handle one, put it in waiting, handle 2, put it in waiting, get it. So alternately you process it. Then you have something called multi-core. Multi-core means I'm able to handle each data independently. Okay, now what happens when you handle data independently? What happens is, you do, this is something, if you remember the model, this is a non-interference model. Okay, you do not have to interfere between each other. Process is more stabilized and faster. Okay, then you have something called multiprocessing. Multiprocessing is when you have one process but you have 2 CPUs available. So what you do, you divide it into 2 equal tasks and then merge it. Okay, that means you achieve the task much more faster. But to carry such kind of a task, the application should be able to handle multiple threads. So this is where CPUs were designed as multi-threaded CPUs. Okay, they were able to handle multiple processes at one time. Okay, then there's something called multi-programming. Multi-programming is when you execute the tasks simultaneously. So there is one task, task 1 and task 2. Both are required to be executed to give an output. So you execute both the tasks at a same time. Okay, that is called multi-programming. And finally, multi-threading exactly means one program can have multiple threads, and each thread can be handled by a single CPU directly. Okay, this is important for CISSP. You should be aware of this concept. Now, as I told you, the moment now, if a processor has to handle so many processes, what happens is there are processing states. So a processor might be in a ready state. Ready state means it is ready to receive data from the primary memory. Okay, and the RAM has multiple tasks waiting at it. This is task 1, task 2, task 3, right? Task 4. So what happens is the CPU is in ready state, right? When it's ready state, it is ready to accept data. And once the data is inside, then it goes into running state. Now, when it is in running state, all the other data, then all the logical unit, it stops any other further data to be pushed into the CPU. Okay. Then once it's completed the task, right, it pushes the task in a waiting mode. It pushes the data back into the memory and goes into waiting mode. Waiting mode is basically it's waiting for some more input. If the task is complete, it pushes it. Otherwise, it is waiting for some more data. Okay. And then it goes to, once it has executed, it waits, and then it goes into supervisory mode. Supervisory mode is it checks whether everything is fine. If everything is fine, it goes into supervisory mode, and then it goes into stopped mode. The process is stopped if it is completed. Okay, so these are the processor states. Now, once it has been processed, there are multiple security rings, logical rings, which are philosophical nature, they are theoretical in nature, right? And that is how kernel protects those complete processing states. So what happens is there is something called a protection ring concept. If you look at your own computer system, you generally do not have access to the kernel. The kernel has access to something called the ring 0. Now, ring 0 is the important hardware and software which the operating system requires to execute its complete functioning. It doesn't want anyone to fiddle with that, right? So it does not give access to anyone. You cannot have access to kernel. The moment you have access to kernel, you have rooted the device. You have touched the operating system. It doesn't maintain its stability anymore. So any kind of malware which can touch this ring 0, okay, are generally called rootkits. Malwares which have the capability to modify the kernel are called rootkits, and they are the most dangerous. Once your operating system has been compromised, more or less your device you can actually throw your device away, because the rootkit has the capability to infect your hardware, the programs which have written on your hardware also. So whenever a laptop or a device has been infected by a rootkit in a very, very fragile environment, that machine will be discarded. Okay. Then after this particular protection ring, the kernel has access to the device drivers. Okay. The most important device drivers for your graphics, not even graphics, for arithmetic and logical units, memory drivers, and other drivers which are critical for it to function. And then there comes the device drivers, which are additional devices which you put and pair with your device. And finally comes the application. So applications have the least amount of privileges to interact with the kernel. Okay, so this is called the protection rings of a system, right? Now, whenever operating systems execute, it has two modes. One is called the privileged mode or the root mode, and one is the user mode. The root mode is the administrator mode. In administrator mode, those who have worked with Linux, it's called the root, right? Or the sudo access. The sudo access gives you additional privileges to install or work with the kernel of the device, but you are still not able to change the kernel. What it gives is the access to do some privileged activity on the system. Okay, user mode is got restricted access, wherein you can just run the system and do not have the permissions to modify a system. Okay, right, this I've told you. Processor states done. Okay, then comes what are the different kind of memory in a system. Okay, so this is all 9th 10th basic sciences. What are the different kind of memory? We have programmable read-only memory. Programmable read-only memory is a type of memory which can be only programmed once. Once you have programmed it, then it is for single use. You cannot change it, right? So what is the implication? Implication is if you want to update it, it will not get updated. So that means if you have a device which has a firmware written inside a prompt, that device is static in nature. It will not have the capability to upgrade its firmware. Okay, it's a class 1 generation device, generally not there anymore. Then you have something called EEPROM. EEPROM is electronically programmable read-only memory. Okay, so such devices, you flash a UV light, you have a device, you flash a UV light, the memory gets erased and then you can write it. Okay, then you have electronically erasable. This EEPROM is called erasable, not electronic. This is erasable programmable read-only memory, erasable by UV light. Then you have EEPROM called electronically erasable. Electronically erasable chips are basically, you have the first chip on which you give a voltage of plus 5 volt, and then you can write on this particular device. Okay, and then if you want to erase it, you have another leg on which you give plus 5 volt, and then you give a erase command, and it is erased. Flash memory is actually many EEPROMs built into your USB device. Okay, your USB device basically has this electronically erasable programmable read-only memory. Your SDD device, that is your SSD devices, solid state devices, are EEPROM devices. Okay, then once you look at computer architecture, it has two kind of RAM. One is the actual physical RAM, which is called the real RAM. Okay, so that might be 8 GB or 16 GB, and then at times the CPU requires some more memory. What it creates is creates a ad hoc memory called cache RAM inside your solid state device or the solid hard drive. Okay, and it allocates this memory to the real RAM. So it increases the memory size which is available to you. It might become slightly slower, but in its addressing space, the CPU has addressing space. It addresses the RAM plus the cache memory. Okay, and then finally you have registers. Registers are nothing but small pieces of memory which are inside the CPU. So CPU at times have certain inbuilt memory in which data stores, and this memory retains the most important data which can be immediately called into the CPU. Okay, and that's how memory works. Okay, so data storage in computer systems, in IT systems, are of three types. First is primary versus secondary. Primary memory, which is accessible by CPU directly, and secondary memory is where you actually store the data, that is your SSD drives or HDD drives, right? Generally, primary memory is volatile. Volatile means once you switch off the system, it is no longer available. And your secondary storage is generally non-volatile. Data is there. Data remnants is there. And finally, there is random versus sequential. Random versus sequential means the CPU can access the memory either sequentially, that is one by one, or it can go and access any slot on the memory. That is called random versus sequential memory. Okay, so there's something called random access memory. Okay, so and there is something called sequential random access memory. So sequential random access memory is basically your RAM is actually sequential. Every time the CPU has to access, it has to go and start from top. Okay, that is called the random memory or sequential memory. So what are the issues with memory security? Generally, non-volatile systems have data remnants, right? You have hard disk in which data can remain for long years. So that's why data remnants is an issue on hard drive. So how do you dispose data? We saw it in domain 2, right? Storage devices have the they get stolen, they get lost. Okay. Whenever you're disposing systems, when it has got end of life and you're disposing those systems, you have to ensure that the removable media is always disposed, and then only you get away with your balance devices. So these days, a lot of electronic trash is being generated. So if you have some critical data, you have to ensure that there is no data remnants from your side. SSDs are known for having permanent data remnants. So the only way you can get rid of data remnants from SSDs is basically to destroy them physically. Okay. Memory, because HDDs, they are magnetic devices. There's something which is moving inside. They have a habit of emanating EM waves, and these EM waves can be caught and translated into information. Such kind of attacks are called tempest attacks, wherein you are trying to put some sensory devices to catch what is happening inside the hard disk of the system, or what is the kind of electronic emanation. When I'm typing a keyboard, it is generating some kind of EM signals, and if somebody is trying to catch those signals, such signals are, such kind of attacks are called tempest attacks. Now, how do you prevent from tempest attacks? You prevent from tempest attacks by Faraday cage. What is a Faraday cage? Faraday cage is nothing but something like your car. Once you remain inside a car, and if there is a lightning strike, you're safe. Why? Because the complete charge is distributed over the car, and through the tires, it is discharged into the ground, and the human being sitting inside remains safe. And that's why they say that whenever there's a lightning strike, you go inside a house, do not stay under a tree or go inside a car, because this acts as a Faraday cage. Basically, it distributes all the electricity on the surface of the car and discharges it through the tires. The tires are also conducting type. Okay, they have certain amount of metal in that. It helps in discharging your car to the ground. Okay, so how do you protect against tempest attacks? You put in critical spaces. The rooms are shielded rooms. Okay, wherein you are working inside, and the shielding provides any EM waves to travel outside. It remains inside the room. Then you can also protect by something called generating white noise. Okay, your device is generating some kind of EM waves, you generate some noise also. Okay, so that if somebody is trying to catch it, they don't come to know which is the real signal. So this is when you generate such kind of noise, it's called white noise. White noise is generally omnipresent. It is the natural noise of this universe. Okay, if you open some kind of a receiver set, you will permanently see there is some kind of energy. That is called the white noise. It's always omnipresent in the universe. You also create control zones. Control zones is if you have certain critical areas, you do not give access to anyone, so that some kind of tempest attack cannot be created. Everybody is working here. You do not allow any devices to come near that control zone. And you also can protect your EM transmission through something called shielding cables. What is shielding cables? You have, say, your cables running, you have a metal shielding on top of that, so that the EM waves are staying inside and gets cancelled out, and they are not emanated outside. Okay, so these are the protection mechanisms for somewhere where you have critical requirement of shielding the EM waves. Okay, a small question, and then we will, this is related to last time, then we will go ahead. Can someone explain why?
So you're typically provided with a virtual private network to have a dedicated access to something which is secure, right? That gives you an unlimited access to, I mean, secure access to it. Now, if I use that access permission to do something for which for an action which is not intended for it, I'm actually violating that trust.
Yeah. So you generally give a VPN to access, internal resources, right? So this is your VPN. So what you do, you use this VPN to go and do access something else. So since the VPN trusts you, you have proven your trust to the VPN, but now you are misusing the VPN to access something else. So that is called a misuse of the transitor trust. Okay. Right. Now, there are a lot of input-output devices in your systems. You should generally be aware. This is basic knowledge. Monitor is output device. Printer is a output device. Keyboard, mice are input devices. Your modems are communication devices which work as input-output both. Now, there are multiple vulnerabilities. Now, monitors, what are the vulnerabilities? Somebody can do shadow, can shadow you and read what you are doing typing. Okay. So that's why you're supposed to have screen guards on your systems. You are not supposed to, supposed to have horizontal separation between two computers. These are basic things which are followed. Okay. Then printers, you should have a clean desk policy. You should not, printing should be controlled, and those who don't require should not be given printers. And there's supposed to be a shredding policy in your organization to protect your information from getting leaked. Okay. Keyboards and mice is, generally they are working on 2.4 gigahertz range, and they have a habit of interfering with each other, and they might give away. If you are using wireless keyboards and mouse, you will see that a lot of information can actually be read using very, very common receivers. Okay. Modems today use WPA3 as enterprise grade security. WPA2 is not considered secure anymore as far as enterprise grade security is concerned. Okay. Then your next thing which protects your system is the firmware. What is the firmware? Firmware is the first place from where the boot of the system happens. Now, if I'm able to corrupt the boot, then my system is compromised right from the root level itself. So nowadays there are a lot of boot protection measures which have come in. One of them is called the silicon root of trust. Okay. Silicon root of trust is a concept which has been implemented in Windows 11. We already discussed this last time. I'm still telling you what happens. The operating system is binded to a device, a chip directly. Okay. That means the chip itself can execute the operating system and a particular type of operating system. If you try to change it, the operating system will not get loaded. This is a particular protection against OS, OS infringement and rootkits. Okay. So what happens once a computer is booted? So it has its CPU. It has a small firmware device which is called a bootloader, which loads the first program inside the CPU. Okay, so it goes, reads the instruction and boots into the CPU. This was the earlier process, and this used to be flawed by rootkits. But nowadays there are a lot of protection measures available. First is called the boot attestation, or something called the secure boot. Okay, in the secure boot, what happens is the boot software is signed by a digital signature. Okay, and the CPU, before loading the boot, checks whether it has been signed by a digital signature from the TPM module. If it is signed, then only it loads the boot software. Otherwise, it doesn't allow. Okay. Then there is something called measured boot. In the measured boot, what happens is, okay, the CPU is loading the software. The boot software has 2-3 parts. It has particular hashes stored in the TPM. It loads the first part, checks the hash, and compares the hash into the TPM. It is fine, then gets the next part. If it is okay, then gets the next part, and then only it executes the boot. That is called a measured boot. Okay. So this is how firmware is protected. Okay. So let's take a short break now. Any doubts till now?
Yes, sir.
Yeah, Uday.
Sir, it's related to TPM and HSM. Yeah,
Yeah.
TPM is endpoint based, isn't it? Whereas the HSM is a server based. The keys,
No,
encrypted keys, where we are storing.
no. See, there is trusted platform module. Okay. Okay. There is HSM. Okay. HSM is the hardware storage module. This is where you actually store the keys. There's nothing to do with the server or client here. Okay. HSM is physically storing the keys inside in a particular hardware.
Okay.
Right. It stores the keys. This is a chip. It's a chip on your PC, which stores your fingerprint data. It stores all the other keys. Okay. On Mac, you can access those keys. Okay. By something called a keychain. Okay. Those keys are embedded, written into the hardware storage module. Okay. Now the TPM is a bigger picture wherein which it incorporates the HSM and the operating system to execute some task in a secure manner. Okay. So it is trusted module which will execute your keys from the HSM. It is a combination of HSM and certain drivers which execute the secure execution of certain key components where keys are involved. Okay.
Okay. Thank you, sir.
Okay.
Thank you for watching. Don't forget to subscribe our channel.